I want to talk a little bit about parameters and method for evaluating a power-to-gas plant and calculation of its annual performance. I'm at the beginning of my research activities at the moment, and I want first to introduce the challenges and the goals of my item. The challenge of the future energy market is to bring in the flexible renewable energies, and one opportunity is to integrate the flexible energy with power to gas, for example. But if you use power to gas, everybody talks about the low efficiency, and also one problem I see is the different flexibility of the electrolyzer unit and the methanation unit. And the goals of the research activities at the moment are to find a systematic method to calculate a comprehensive and predictive assessment of a power-to-gas system, and find for specific locations and applications a tailor-made power-to-gas plant. The idea behind this is to reduce CAPEX and OPEX and to rise the operation hours of the methanation plant, because the flexibility of the methanation plant is lower than the flexibility of all electrolyzers. At the moment, for example, the companies which sell power-to-gas plants make feasibility studies with only a few variables. This is the installed power, the estimated operation hours, and the output of S&G, and the operation and maintenance cost, for example. So the output is the methane, the input is electricity and heat, and they calculate a few hours of operation. The advanced feasibility studies, they have a few more variables. For example, you can look at the volume of purchased electricity. You can divide the system, the power-to-gas system, into the subsystem electrolyzer, store the hydrogen in a storage, and then you can have the methanation unit. So the demand of the electrolyzer and the demand of the methanation can be different, and depend on the location or the volume of purchased electricity. The hydrogen storage is smaller or bigger. Also, you can use the min-max load of the electrolyzer to have a variable operation of both subsystems. One opportunity, of course, is to use also the waste heat, but I tell you later something about that. And in my research activities, I calculated with a new character for power to gas. I think in other areas the character is well known. I call it the annual performance, and the annual performance is the output of the power-to-gas plant, so it's the S&G and optional the heat of the electrolyzer and the heat of the methanation unit, divided through the input, so the input of the power and heat of the electrolyzer and the power of the methanation unit. I told you in this way, and also the input is that the electrolyzer and the methanation unit can have under operation different states. For example, here you see you have a cold standby. If the methanation, for example, is not running for a long time, you should not heat it or keep it warm. So you can bring it in the modus cold standby, heat it up, and bring it into service or the production mode. The output, I told you before, is first S&G, not America, first S&G, second the use of waste heat, because a power-to-gas plant has the goal to produce S&G and not heat. If you want to have a higher efficiency and use heat, you can do power-to-heat, not power-to-gas. Okay, I have bring you two examples. Power-to-gas plant, for example, in Rapperswil, where the University of Applied Science is. I size power-to-gas plant, for example, a PV 1 megawatt plant and 1 megawatt wind turbine in Rapperswil. I think everybody knows maybe the wind in Rapperswil is not the best area, or for wind, Rapperswil is not the best area, but to have an example, I choose these two renewable energy input sources. So on this picture you see downstairs here, this is the wind profile, and the orange one is the demand of the whole power-to-gas system, so the electrolyzer unit and the methanation unit. And in blue, you see the demand of the methanation unit. So the peaks are heating up the power-to-gas, the methanation unit from cold standby to hot standby. And then here you see different stages of operation. Or here a little bit zooming in. Here the methanation unit is off because the black line is the storage of hydrogen, because the hydrogen storage is empty and not enough hydrogen is produced to run the system. So the wind turbine is running with only 200 or 300 kilowatts per hour, and then the hydrogen storage will be filled up here. Maybe I can show. No. It's filled up until a specific amount, and then the methanation starts, operate for a few hours, and then come down again to the cold standby mode. And this happens all the time over the whole year. For example, at the top you see it with PV electricity as an input. At the night, the sun is not shining, of course. No hydrogen is produced, but the methanation is still running because of the hydrogen in the hydrogen storage. And if you compare these two plant application, you see the demand of electrolyzer is the same. The size of the hydrogen storage is different. I decide the size to have a high amount of operation hours from the methanation unit. So you see here the methanation unit, if you have a PV plant, is more than 6,000 hours, and the operation hours of the electrolyzer is next to 3,000 hours only. But you see also the electrolyzer and the methanation both have to be bringing into service and bring down to a cold or hot standby. It depends. And the production of SNG is also different. But what is the idea behind? If you calculate this system in a normal way with the efficiency of the steady state models, then you have an efficiency of 43%. And if you calculate it with the annual performance without optimization, you have an efficiency, or I call it annual performance, of 26%. And if you adapt the system and optimize it, so the size of the methanation, for example, you see here it's 250 kilowatts per thermal hydrogen. So and the electrolyzer has 1,000 kilowatts. So you have a much smaller methanation unit than the electrolyzer. With this optimization, your annual performance rise up to 33%. And if you compare it or go on with this calculation, you have more realistic calculation of the gas production cost. And these are the next steps, and smoothen. My next steps are also to smooth the model and make it more easy to calculate with on different locations or different electricity input sources. Yeah, thank you for listening.